So I think we're streaming. Are we streaming? Alright, it seems like we're streaming. Okay. Good to know. Alright, so we're on project 75. So less than 1/4 the way there. Well, more to go. Okay. And last of the iterator patterns. Oh my gosh, I have threads and clippy. Alright. Let's define a simple model to track rustling experience progress. Didn't we already do this? We might. Oh, we are. We're in box pointers. We're in smart pointer land. Okay, cool. That's real cool. I'm interested because my understanding is everything's referenced and has an owner, so I don't actually know what smart pointers would be here. So in Rust, smart pointers are variables that contain an address in memory and reference some kind of other data, but they also have additional metadata and capabilities. Smart pointers in Rust often own the data they point to, while references only borrow data. Okay. So let's see where we're at. In this exercise, we are given a bank of 32s called number with values ranging from 0 to 99. We would like to use this set of numbers within 8 different threads simultaneously. Each thread is going to get the sum of every 8th value with an offset. The first thread, offset of 0, offset of 1, offset of 2, offset of 7. Each thread should own a reference counterpoint to the vector of numbers, but RC isn't thread safe. Therefore, we need to use arc. RC. What is RC? Is that a value? Reference. Oh, but reference counting isn't thread safe. Therefore, we need to use arc. Don't get distracted by how threads are spawned and joined. We'll practice that later in the exercise about threads. So this is arc. What does the A stand for in arc? Asynchronous reference counting? To define a shared number by using arc, let's shared number. All right, we need to check out some resources here. We're gonna need to do some reading. Smart pointers. Box. So what is arc? Reference counting and smart corners. Okay, well, maybe I should just look up how to use arc. Arc Rust sample. Arc. When shared ownership between threads is needed, arc atomically reference counting can be used. This structure via the clone implementation can create a reference pointer for the location of the value of memory heap while increasing the reference count. As it shares ownership between threads, when the last reference pointer to a value is out of scope, the value is dropped. Okay, so it looks like I just do so let's see. So I want shared number what is shared number supposed to be? Is it a reference to? Shared number. What? So this join handler. So it's spawning a thread. Child number. So this is where I'm supposed to give it 0. So my brain wants to say arc new number. So I think I need to so I need some help from my iteration here. So I need not map. There should be something that says I want to filter. So editor. Now my mind says this is going to create a new I think I need some help here. I don't actually understand. The compiler message should help since you cannot store the value versus types. We need to store the reference pointer to. Alright, let's bring this back to beginning. So you're on box 1. Okay, so let's do box 1. At compile time, Rust needs to know how much space a type takes up. This becomes problematic for recursive types where a value can have as part of itself another value of the same type. To get around this issue, we can use a box, a smart pointer used to store data on the heap, which also allows us to wrap a recursive type. The recursive type we're implementing in this exercise is called a cons list, a data structure frequently found in functional programming languages. Each item in the cons list contains 2 elements, the value of the current and the next item. It's basically a linked list in my mind. Okay. So, recursive without indirection. So here's the reference counting thing again. Oh, stupid. Okay, so we create a box. Create, would I just return nil? Create an empty list. So in my mind, it would just be no. So list. But I don't think that's what it wants. Okay. It's not equal. So this would take, I'm assuming anything. List dot then a box list. Okay, should work. All right, cool. Perfect. RC1. In this exercise, we want to express the concept of multiple ownership via the RCT type. This is a model of our solar system. There is a sun type and multiple planets. The planets take ownership of the sun, indicating that they revolve around the sun. Oof. Spreading their propaganda. Alright, let's see. Okay. To do. Do I just... So you want to create a new sun? Okay, so you want me to continue to clone this, is from my understanding. So now you have 7 references. And now you just drop them. So, drop. Whoa. Oh, so then we go inverse. So Mercury would be on the bottom. Venus. And Earth. Did not grab my copy. ice crystal. Earth. Alright. Arc 1. So now we're back to where I should be. So, this is where I need help. Make a shared number be an arc from the numbers vector. Then in order to avoid creating a copy of numbers, you'll need to create child numbers inside the loop, but still in the main thread. Okay, we're going to try new arc. What's that? Arc new. Okay. And then they said should be a clone. Oh. Huh. So your counter. You're a copy of a counter. So this interesting. Okay. So RC, I wonder if there's a strong count, if I can do a strong count. Can do R. Join. Oh, share number. Okay, I'm gonna do. Huh. Interesting. So, so when we do this, if I did put this here, okay, so but then I can still do this. Oh, so this is where it actually... Okay. So this pushes it up. Okay. So I could do something fun like this, and I could see. Oh, interesting. So join handle. It only has a 1. So it clones it here. Not entirely sure. Not entirely obvious to me. The cow. This exercise explores the cow. Clone on right, smart pointer. It can enclose and provide immutable access to borrowed data and clone the data lazily when mutating or ownership is required. This type is designed to work with general borrowed data via the borrow trait. Borrow the cow. Okay. So, let's see what I need to tackle. Reference no mutation. Did you replace with cow owned? Cow from. So, clone the vector if not already owned. So we're doing the exact. We're a cow. It says no mutation, so we're gonna borrow it. Owned, no mutations. I don't understand. These are all, is it the data that's changed? Alright, we're just gonna see what happens. Did I just guess it right? Huh. This is not. So you're saying if I just grab this back, it would pass. So this is a property. It's okay if it's trying to see if it's owned or borrowed. So if the value is less than, it has to be owned. Okay, so how do you differ here? So if I was to do here looks the same. From, oh, okay. So this is from a reference to the vec. This is from a vec. So this should be copying it. So cat owns it directly. In this case, no mutation occurs. All numbers are, and thus no clone. But the result is still owned because it has never borrowed or mutated. Okay. And of course, this is the case if the mutation does occur. Not all numbers are absolute. In this case, the call to in the absolute function returns a reference to the same data as before. Huh, okay. Alright, interesting. That's something that I need to delve into, because that is not apparent. In most current operating systems, in executed programs code, current operating systems, and executed program code is run in a process. In the operating system, manage multiple processes at once. Within your program, you can also have independent parts that run simultaneously. This feature that runs these independent parts are called threads. Alright. Close to the right. Threads. This program spawns multiple threads that each run for at least 250 microseconds. And each thread returns how much time it took to complete. The program should wait until all the spawn threads have finished and should collect the value returned into the vector. Okay. Elapsed time is milliseconds. Okay. Use the join handle. Use the join struct, which is returned by the thread. So push the handle. So let's look at the example we had in Arc. So I need to join. Okay. So I handle dot join. Test. Let's see what this is. It's a dino. Okay, that makes sense. Okay. So I could just unwrap it, I guess. So results push. Now, how would they have handled this? I'm pretty sure I was lazy. Okay, no. Fair enough. Alright, so close. Only 15 more to go. We'll actually finish this up this week. Probably finish it up. Building on the last exercise, we want all of the threads to complete their work. But this time, the spawn threads need to be in charge of updating a shared value. Oh my god. Okay. We must take an action before you update a shared. Okay. This is a read section for sure. Let's see. ToString. Dining. I don't know what the dining philosophy is. This paper. This paper. This paper is 260 pages. Too long for me. Inline assembly. It's kind of cool. Supports inline assembly to do the DCC incline. Using threads to run code simultaneously. Okay. This looks very C. Transfer data between threads. So we're not doing that. Shared state. Does this guy have mutex? Arc isn't enough, you want a mutable shared. To do, you must take an action for updating a shared object. Do I need a mutex? What's my hint? Defer. Okay. Arc is an atomic reference counterpoint and allows safe shared access to mutable data. But we want to change the number to job done, so we'll need to also use another type that will also allow one thread to mutate the data at a time. Take a look at this section of the book. Keep reading if you like. Oh, okay. Atomic reference counting. Ah, shit. I keep... Shared state. Fortunately, ARCT is a type like RC type that is safe to use in concurrent situations. The A stands for atomic, means that is atomic reference count. Atomics are an additional kind of concurrent primitive that we won't cover in detail here. See the standard documentation for atomics for more detail. At this point, you just need to know that atomics work like primitive types but are safe to share across threads. You might then wonder why all primitive types are atomic and why standard libraries types aren't implemented using ARCT protocol. The reason is that thread safe comes with performance penalties that you only want to pay when you really need it. If you're just performing operations on values with a single thread, you can run it faster, enforcing the guarantee atomic provider. So fix programs by changing the use line with a new call to clone founding run. So we take the mutex new. So mutex new. So we're going to clone the counter. Okay, so my thought is we're going to use mutexes. Oh, so needy. What? Sync. So we need mutex new job T. That's not enough. Okay, so my thought would be that would where counter. So they have shared state dot block and then I can do status s dot job print the value of job. Okay. Job status. What is job status? Do I have to? I'm not. Do I? Do I have to? Lock it? Huh. I guess that makes sense. So what beautiful syntax am I missing? Just so interesting to know what Clippies are. Code so you can catch common spikes and improve your Rust code. If you use the installation script for Rust, and Clippies should be already installed. Rust stuff. Add Clippies. Collection of lint hints to catch the most harm. There are 750 lints included in this crate. Lints are divided into categories, each with a default init level. To annoy/help you changing the lint level. Okay, let me look at Clippies. Fix the Clippy hint. Oh. So I don't have to do anything. I don't have to like enable Clippy. Okay, macros. Alright, I think I gotta do some more reading, so we'll come back. Alright, I need some food. I have food poisoning, so a lack of food poisoning.